Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. What is a comet? For over half a century, the standard astronomical model has stated that comets are primordial aggregates of ices and dust, or dirty snowballs, that formed roughly 4.5 billion years ago in our solar system's infancy. In this model, sublimating ices due to solar warming is responsible for most comet activity, including the comet's jets and coma. However, countless observations of comets going back well over a century, as well as the data from every comet mission to date, have only raised doubt about the validity of this model. In 2015, the ESA's Rosetta mission to Comet 67P did nothing to erase these doubts, but rather, the findings have only confirmed the need for a radical new perspective on the very nature of comets. How many of the great comet mysteries, both old and new, might be resolved if an electrical theory of comets is correct? In recent years, Dr. Franklin Anariba, a specialist in electrochemistry at Singapore University of Technology and Design, has investigated the evidence for electrochemical reactions on comets. In this video compilation of 5 recent interviews, Dr. Anariba analyzes the latest papers from the Rosetta mission, which provide stunning direct evidence for electrical comet activity, evidence which may prove to be a game changer in comet science.
Let me provide a context for this episode series on Comet 67P. The Rosetta mission is providing us with a plethora of scientific reports filled with very valuable information on the composition of the coma and nucleus of Comet 67P, Churyumov-Gerasimenko, hereafter referred to as 67P. In this episode series, I intend to pinpoint relevant findings from different published scientific articles that are relevant from the perspective of the electric universe. It is a critical review that recognizes the significant contributions of all authors where no misrepresentation is intended, and which overall purpose is to inform the general audience of an alternative interpretation of the reported findings. This is accomplished by commenting on recent findings reported using various instruments and techniques, including the Rosetta Plasma Consortium Ion and Electron Sensor, Rosetta Plasma Consortium Ion Composition Analyzer, which is a mass spectrometer capable of detecting positive ions or cations, and the Rosetta Orbiter Spectrometer for Neutral Analysis Cometary Pressure Sensor. My analysis is derived from the observations made on Comet 67P at heliocentric distances of 2 to 4 astronomical units. At such heliocentric distances, Comet 67P displays low cometary activity as it is far from reaching perihelion. But this fact might be decisive in elucidating phenomena that otherwise would be convoluted and difficult to discern. My commentary is based on reported data and interpretation of same by the authors, which on occasion I reinterpret from the perspective of someone with an electrochemical background. As can be ascertained by reading most of the reported published scientific journals on Comet 67P, the main paradigm is the one proposed by Whipple some time ago, which could be called the condensation sublimation model. I'm not here to refute this model, which I recognize to be of importance near perihelion distances if comets were to contain large amounts of volatile ices on their surface or in their subsurface. Instead, my intention is to bring to everybody's attention that there could be other mechanisms at work for the origin of water and other chemical species in the cometary coma. One mechanism is proton implantation, which has been recalled to explain water ice presence in craters in the moon, can be invoked to explain the presence of small amounts of water ices on the surface of comets with tenuous ion density in their comas. Another mechanism, mostly unknown to the astronomical community, is based on electrochemical principles, which I have named electron stripping. These mechanisms can be dominant at larger heliocentric distances away from perihelion, Well, the voltage differential between the comet and the surrounding plasma sheath of the sun can be largest. These mechanisms can be recalled to explain the presence of water vapor in the common comets. The invocation of these two other mechanisms is necessary because so far no significant amount of water ices have been identified on the surface and in the subsurface of the nucleus of Comet 67P. Furthermore, the recent findings of molecular oxygen on the comets of Comet 67P, along with its link with origin and presence of water vapor, points to the presence of an electrochemical method of production. Before I continue on to discuss the various findings, it is important to clarify and define important terminology used in the current condensation sublimation model for cometary origin and its relationship to the plasma environment near the nucleus of comets. In this model, the solar wind-associated interplanetary magnetic field interacts with comets' coma, creating a bioshock due to the pile-up of magnetic fields on the sunward direction of the comet. According to the current proposed mechanism, an induced magnetosphere forms at the interface of the solar wind and comet's plasma sheath, which is partially ionized and electrically conducting. This phenomenon is mostly observed near perihelion, when comets in general display high cometary activity. Equally important to this model, neutral gas molecules in the coma are thought to sublimate from the nucleus and then undergo photoionization by extreme ultraviolet radiation emanating from the sun, resulting in charge separation and the formation of the plasma sheath surrounding the nucleus. In addition, the solar wind, which is comprised of cations such as protons and alpha particles, such as helium-2+, and electrons, is thought to play an important role in the ion gas production via sputtering on the surface of the nucleus and ensuing charge exchange mechanisms. Mass loading is thought to occur concurrently when newly formed gas ions initially traveling at low speed, approximately 1 kilometer per second, are picked up or accelerated by the solar wind-associated interplanetary electric field to its mean speed of approximately 400 kilometers per second. Mass loading becomes significant at distances less than 1,000 kilometers from the nucleus. A typical mean solar wind speed ranges from 300 to 600 kilometers per second. This kinetic energy can be translated into potential energy by equating both energies to the following equation. Potential energy is equal to kinetic energy, which is equal to 1/2 times the mass of the proton times the velocity of the proton square. We can use this equality to realize that a solar wind speed of 300 to 600 kilometers per second is equivalent to 470.4 to 1881.7 electron volts. For reference, the ionization potential of a gas hydrogen atom, where the hydrogen dissociates into a proton and an electron, is 13.6 electron volts. The Lorentz force is responsible for accelerating newborn ions orthogonally to the solar wind direction and the interplanetary magnetic field, and causes the ions to gyrate around and along interplanetary magnetic field lines, forming a ring distribution. One of the consequences of this mass loading or pickup ion action is the deceleration of the solar wind to the conservation of momentum and the excitation of cyclotron wave activity. The gyration of the ions around the solar wind can be characterized via the Larmor cyclotron parameters, such as radius of gyration is equal to the mass of the ion times the velocity of the ion divided by the electric charge times the solar wind magnetic field. The period of gyration is equal to 2 pi times the radius of gyration, all divided by the velocity of the ion. The cyclotron or gyro frequency is going to be then equal to 1 over the period of gyration. And the angular cyclotron frequency is equal to the electric charge times the solar wind magnetic field, all divided by the mass of the ion. With these general concepts in mind, I would like to take a look at two important recent reports on the dynamics of the comet's plasma environment. In the manuscript titled Observations of a New Type of Low-Frequency Waves at Comet 67P, Churyumov-Gerasimenko by Richter et al., which measured the plasma environment in the coma as close as 10 kilometers, the general observations reveal a significant ion and electron activity within the inner coma on the comet. The relevant findings are summarized below. 1. The solar wind carries a detectable magnetic field of approximately 2 nanotesla, while the magnetic field in the inner coma of 67P show a value of approximately 4 nanotesla, indicating that the magnetic field energy density was higher close to the nucleus. Magnetic field oscillations at approximately 40 millihertz dominate the immediate plasma environment of the nucleus and show no preferred propagation direction. An electric current density of 4.8 nanoamps per meter squared was determined. The findings are of particular interest and intriguing. First, electrical activity in the nucleus of the comet is discerned. Second, most of the ions detected in the cometary coma of 67P are thought to be water cations, which display a cyclotron frequency in the range of 0.8 to 3.5 millihertz, much different from the dominant 40 millihertz detected. This result is unexpected, indicating a new mechanism must be in action. The authors add, and I quote, "It should be noted that the suggested wave source is not co-moving with the solar wind flow. The wave source is almost fixed in the nucleus frame of reference." End of quote. The authors discard the classical pickup ion instability as the source of the magnetic oscillations and instead propose that photoionized ions move transverse to the magnetic field but along the solar wind, which flows in the direction of the electric field, in what is called a cross-field electric current density. In other words, the electric fields control cometary ion motion, but in a different way from the known mass loading action. In the report by Nilsson et al. Titled Evolution of the Ion Environment of Comet 67P, Churyumov-Gerasimenko, whereby the plasma environment is measured using the ion composition analyzer mass spectrometer, capable of measuring positive ions, the following findings are of attention. 1. Cometary ions detected are mostly water cations with two distinct potential energies. Cold water ions contain potential energies of approximately 10 to 50 electron volts and traveling from an area between the sun and the nucleus, while the accelerated water ions contains potential energies of approximately 120 to 5,000 electron volts and are detected coming from the direction of the sun. Water ion flux increase by 4 orders of magnitude when the heliocentric distance decreases from 3.6 to 2.0 astronomical units, and the solar flux only increased by a factor of 2. The solar wind did not slow down noticeably, suggesting mass loading is negligible. Interestingly, the authors add, open quote, "A simple scenario would be that the pickup ions initially move along the undisturbed solar wind electric field, while the newly created electrons drift, causing a charge separation. The electric field of the charge separation will initially have a component opposite to the solar wind electric field and a component in the anti-sunward direction. This is consistent with both the flow of the water ions and the observed deflection of the solar wind." End of quote. The implications are threefold. A. Charge separation is due to an electric field, which is an indication of the presence of a voltage differential. B. If the accelerated water ions are traveling from the direction of the sun, electrons must be traveling in the direction towards the sun. C. The high water cation flux production rate may be an indication that another process is at work besides the traditional proposed photoionization due to ultraviolet radiation. To summarize episode 1, taking together the overall findings paint a picture of a highly dynamical plasma environment in the vicinity of the nucleus with potential consequences such as charge separation of cations and anions due to a voltage differential.
In episode 2, Dr. Anariba explores the significance of the direct measurements of fast-moving electrons and electric fields in the plasma environment near the nucleus of Comet 67P. As Dr. Anariba explains, these discoveries indicate the existence of a, quote, voltage differential, which is all that is required for significant electrochemical reactions to occur on a comet.
In episode 2 of this series, I expand on the presence of electrical activity in the vicinity of the nucleus of Comet 67P. This is done by commenting on two important recent reports. In a manuscript titled The Rosetta Ion and Electron Sensor, IES, Measurement of the Development of Pickup Ions from Comet 67P, Churyumov-Gerasimenko by Golsan et al., the plasma environment is scrutinized at a heliocentric distance of 3.5 astronomical units and at 28 kilometers from the nucleus of the comet. In summary, the authors report: 1. Detection of low-energy water cation population for the first time in a weakly outgassing comet far from the Sun. 2. Water cation populations detected display 10 varying distributions. 3. No angular distribution is observed for the water cation populations, suggesting that these ions are created locally and have not been accelerated by the solar wind electric field as expected with mass loading. 4. Interestingly, mass-loaded ions and solar wind protons move in opposite direction, while electrons remain unaffected. The implications of these findings reside on the assumptions that mass loading plays an important role at such large heliocentric distances on a comet with a tenuous coma density. For instance, it has been reported that the solar wind ions are deflected but not slowed down as expected during a mass loading process, suggesting that mass loading is negligible. Therefore, these findings instead can be interpreted to indicate a complex and dynamical electron-rich environment near the nucleus at such large heliocentric distances where mass loading is negligible, suggesting another ion motion mechanism is dominant. In this line of thinking, of utmost interest is the paper by Clark et al. Titled Suprathermal Electron Environment of Comet 67P, Churyumov-Gerasimenko, Observations from the Rosetta Ion and Electron Sensor. The term suprathermal implies highly heated electrons possessing high kinetic energy. In the manuscript, according to the authors, suprathermal fast-moving electrons are accelerated by unknown mechanism from a few electron volts upwards to hundreds of electron volts and play an important role in the electron-neutral chemistry as well as the dust grain charging. Moreover, previous studies show that these accelerated electrons are ubiquitous, but could not agree on a particular mechanism. Several accelerating electron mechanisms have been put forth. 1. Suprathermal electrons are likely associated with upstream cyclotron wave fluctuations convecting tailwards. In other words, the accelerating energy is provided by mass-loaded ions traveling from the direction of the Sun towards the tail of the coma. 2. Suprathermal electrons are accelerated in a similar manner as electrons behind interplanetary collisionless bow shocks. 3. The active magnetospheric particle trace explorer satellite showed that lower hybrid cyclotron waves from mass-loaded ions were responsible for the electrons. Hybrid refers to cyclotron frequencies in between a proton and an electron. Some studies ascribe suprathermal electron acceleration to photoionization, while other studies indicate the role of photoionization to be negligible. It is then clear that there is no agreement on the dominant mechanism behind suprathermal electron acceleration, more so for Comet 67P, which has a 100 times lower coma density than Comet Halley. In this context, the authors inform: number 1, a highly dynamic suprathermal electron cloud consistent with observations of peak comet activity near 1 astronomical unit. The authors add, it is surprising that a weakly Gaussian comet at a large heliocentric distance produces a dynamic and energetic superthermal electron environment. 2. Electron densities near the nucleus are in a range of 10 to 100 per centimeter cubic. Taking into consideration that the comet 67P was approximately 3 astronomical units at the time of the observations and displayed a tenuous coma, which contradicts all previous expectations, it is very likely that another mechanism for accelerating electrons near the nucleus is in action. The report continues on considering potential mechanisms for which processes account for the density and flux enhancement that the ion and electron sensor observes are not obvious. For instance, 1. Photoelectrons play a role by ionizing molecules and creating energetic secondary ions via photoelectron impact dissociation. 2. In bipolar electric field, the authors comment that, open quote, if a well-structured electric field were present, then a well-defined peak would be expected. Again, this points to a fine structure in the plasma environment. End of quote. The implications are that the electric field is filamentary in nature. 3. Acceleration caused by cross-shock potentials. Interesting enough, a cross-shock potential, which has been observed to accelerate electrons, can be thought of as a double layer in an electrochemical experiment. However, there's no evidence for a bow shock or a reverse bow shock at a heliocentric distance of 3.5 astronomical units. 4. Magnetic field compression. However, there was no data on the direction and magnitude of the solar wind-associated magnetic field. 5. Lower hybrid cyclotron waves due to mass-loaded ions. The authors settled for this explanation to explain their data. Surprisingly, the authors conclude that the superthermal electrons are being accelerated by an admixture of photoelectrons and cyclotron waves produced by pickup or mass-loaded ion instability. Their conclusion is contradictory because in the text, the authors report on a rich and dynamic electron cloud, indicating a high density of electrons in the vicinity of the nucleus, even though Comet 67P displays a tenuous coma density. Hence, the question is, where are the electrons coming from? Another contradiction is that mass loading associated with the solar wind means speed deceleration. However, the authors state that, and open quote, the ion data do not show a significant deceleration of the solar wind, close quote, suggesting that ion mass loading by the solar wind is negligible. In addition, the authors write that, open quote, unfortunately, there's no instrument on board Rosetta that can measure electromagnetic waves at this frequency, close quote, referring to lower hybrid cyclotron frequencies. These observations might indicate that their conclusion is premature. From an electrical perspective, electron acceleration is due to a point charge sitting on an electric field, which is an indication of the presence of a voltage differential.
In episode 3, Dr. Anna Reba penetrates to the heart of a likely major misunderstanding in comet science, and that is the interpretation of spectroscopic data as proof that comets are icy bodies. As Dr. Anna Reba explains, the data gathered by the Rosetta instruments demand a new explanation for comet water production, as well as the production of surprising abundances of various compounds.
In episode 3, I address a potential relationship between solar wind sputtering on the surface, the detection of metal ions, and water production. Currently, there are 5 processes thought to be responsible for extracting alkali atoms from the surface of comets. 1. Thermal desorption. 2. Photon-stimulated desorption. 3. Solar wind sputtering. 4. Micrometeoroid vaporization. 5. Photodissociation of parent molecules. In the manuscript titled Solar Wind Sputtering of Dust on the Surface of 67P, Churyumov-Gerasimenko by Wirtz et al., a double focusing mass spectrometer is used to detect neutral volatiles in the coma, which are not expected to be sublimated or partially sublimated, such as sodium, potassium, silicon, calcium, and sulfur. Their findings can be summarized as follows. 1. Silicon is the most dominant species observed by the mass spectrometer, which is reasonable since it has been shown that Comet 67P is comprised of refractory minerals such as olivine. Two, most of the species are detected from above less illuminated areas in the nucleus of the comet. That is, the winter hemisphere. Three, in comparison to carbonaceous chondrites, Comet 67P shows sodium abundance, calcium depletion, and potassium excess. The summary is that detected neutral metal fluxes are the result of solar wind sputtering on the surface of the nucleus from the winter hemisphere, indicating areas of high erosion activity, such as the neck region, appear unaffected. Solar wind sputtering can explain dust jets and water ice formation in less illuminated areas of the comet, but not those areas facing the sun, as the solar wind does not penetrate through the plasma sheath of the comet. These findings suggest another mechanism must be at work along with solar wind sputtering to generate all of the dust found in the comet. A corollary of this study is that proton ion implantation is more likely to occur in areas of less illumination. Let's keep in mind that the microwave instrument for Rosetta Orbiter, MIRROR, months ago did not find significant water ice on the surface of Comet 67P. In the article titled "The Diurnal Cycle of Water Ice on Comet 67P, Churyumov-Gerasimenko" by DeSanctis et al., a water ice cycle is proposed based on measurements using infrared spectroscopy. In this study, the infrared reflectance spectra taken from various levels of illuminated regions of the surface of Comet 67P reveals 1. A broad absorption band at 2.8 to 3.6 micrometers attributed to organic compounds. 2. The absence of pure water ice absorption bands indicates an upper limit of about 1% by volume of water ice at the instrumental resolution. 3a, open quote, flattening of the continuous slope and reduced thermal emission as the 3 micrometer band depth increases, end quote, suggesting exposed water ice in addition to organic materials. On the basis of these observations, the authors use a scattering theory to model the infrared reflectance spectra as an intimate mixture of water ice and organics to derive water ice abundance maps. In order to fit the data, the model required for relative water ice abundance in the mixture to be 10 to 15%. This kind of particular analysis of modeling empirical observation is quite acceptable in the scientific community, and the authors here make reasonable assumptions to fit the data. However, the strength of a model is measured by the assumptions made. Subsequently, from the modeling, the authors extract water ice abundance maps and propose, open quote, direct condensation of gas, sublimation from the subsurface under appropriate thermodynamic conditions, end quote. By thermodynamic condition, they also imply a temperature inversion mechanism, which works more or less like this. Water ice in the water organic mixture sublimates from the uppermost surface layers. When this surface is not illuminated by the sun, such as shadows or nighttime, a temperature inversion occurs between the now colder top surface layer and interior layers a few centimeters deep. Water vapor in the warmer interior layers diffuses upwards and condenses in the uppermost colder layer, where it sits stably until it is illuminated again, upon which the water ice undergoes sublimation. Then the cycle repeats again. It is beneficial to place the study in a wider context. Although based on the title of the manuscript, one might think that there is water ice on the surface of the nucleus of Comet 67P, the authors clearly state that A, open quote, it must be mentioned that the contribution to the total outgassing from this surface layer is limited in time, end quote. B, open quote, the amount of water flux coming from the superficial ice documented by Burtis represents approximately 3% of the total water flux measured by MIRROR. Vertex uses infrared emission spectroscopy, while Mirror uses microwave spectroscopy. In other words, this mechanism represents a very small percentage of the total water presence on the surface of the nucleus, or in the coma. A quick analysis of these findings and the observations reported on solar sputtering mentioned earlier leads me to think that solar sputtering can play a role in the water ice observations for the following reasons. A. According to the derived water ice abundance maps, only small amounts of water ice are detected on the surface. B. Water ice seems to be replenished in regions of lesser illumination, such as shadows or nighttime. And C. Solar sputter has been shown to be effective in areas of lesser illumination. Taken together, it is reasonable to attribute the observed water ice formed in less illuminated areas to proton implantation into refractory silicates, where they interact with oxygen atoms located in the refractory silicate lattice structures. This is not unusual, as it has already been demonstrated to occur in laboratory experiments and thought to be the dominant mechanism for water ice found on crater rims on the moon.
In this fourth episode, Dr. Anna Reba discusses one of the most significant discoveries of the Rosetta mission, and that is the ejection of negatively charged dust grains from the comet nucleus. Dr. Anna Reba explains why this discovery so strongly supports his theoretical framework that a voltage differential between the comet and its surrounding plasma sheath is the driving force for electrochemical reactions at the comet.
In episode 4, I addressed the nature and charge of detecting nanograins in the coma of comets. An interesting article put forth is that of Gambosi et al. Titled Negatively Charged Nanodust Grains at 67P Churyumov-Gerasimenko. The main findings in this manuscript are quite interesting and summarized as follows. 1. The ion and electron sensor detected nanograins with nearly monoenergetic beams in the 200 to 500 electron-volt range. 2. These nanograins, which authors attribute to water nanograins, 3 to 4 nanometers in diameter, were negatively charged and were traveling away from the nucleus of the comet in the sunward direction. 3. Moreover, no signal for positive charged nanograins was detected by the sensor. The authors explain the observations via the folding umbrella pattern of those nanograins. In this reasoning, water nanograins are dragged out by gas outflow, which are then pushed back in the direction of the nucleus by radiation pressure. But this attribution is problematic and to some degree contradictory for the following reasons. The following umbrella pattern will indicate dust nanograins travel towards the nucleus, thus contradicting the observation that the negatively charged dust nanograins were moving from the direction of the nucleus when detected. The lack of detection of positively charged nanograins is attributed to photoionization near the nucleus of the comet to form negatively charged particles. However, if photoelectron impact dissociation ionization mechanism is considered, as previously published in Measurements of the Near Nuclear Coma of Comet 67P Churyumov-Gerasimenko with ALICE ultraviolet spectrograph on Rosetta, positive ions would have been generated and should have been detected. Finally, the authors attributed the lack of signal for positively charged dust nanograins to an instrumental failure. In a wider context, the explanation given is unsatisfactory. A different but feasible interpretation is put forth. The dust nanograins are being charged from electrons originated from the surface of the nucleus because, as I have presented in previous episodes, there are plenty of accounted electrons in the vicinity of the nucleus not attributed to photoionization. Instead, I propose these electrons are a consequence of the electron stripping process driven by a voltage differential between the nucleus and the comet surroundings. Further support for this theoretical framework is revealed in a study of comet Pan-STARRS, which was analyzed using white light when the comet was at a heliocentric distance of 0.3 astronomical units close to perihelion. In the report by Rafi et al., dynamics or high-velocity evanescent clumps emitted from Comet C 2011 F4, observed by stereo, highly dynamic ejecta traveling in near radial anti-sunward direction is observed. The traditional view has been that along with volatile species, dust particles with varying sizes are ejected into the cometary coma and subjected to a wide range of physical processes such as gravity, radiation pressure, fragmentation, charging, and collisions. The ejected clumps are found to have an initial speed of 200 to 400 kilometers per second, which is then accelerated to 600 kilometers per second. Furthermore, the stereo images morphology suggests that particles less than 1 micron are swept radially in the anti-sunward direction, regardless of the ejection times and locations along the comet's orbit, while particles greater than 1 micrometer flow into the dust tail forming stria. And although solar radiation plays a role in size sorting of the grains into dust, ion, and neutral tails, it cannot accelerate to velocities greater than 200 kilometers per second in the observed time interval and distance. For instance, a 1 micrometer cluster to be accelerated by radiation pressure to a velocity of 350 kilometers per second in a distance of 10 to the 8 kilometers requires approximately 2,700,000 seconds. Instead, a faster acceleration is seen, needing only 20,000 seconds. As a result, they also suggest that radiation pressure plays no role in the acceleration of the ejecta with sizes less than 1 micrometer, but instead, the ejecta is charged by photoionization and picked up through mass loading by the heliocentric electric fields. After a long and careful analysis, the authors conclude that 1. Nanograins are comprised of positive cations, especially containing low ionization metallic ions, sodium plus, potassium plus, and neutral, sodium, potassium, lithium, calcium species. 2. Provided the nanograins were singly charged, a cluster of 5 olivine molecules with a radius of 1.4 nanometers is able to explain the observations. Subject to confirmation, the one-to-one relationship between the clumps and stria might indicate the presence of filamentary electric fields in the vicinity of comet's tail. These findings are of particular importance since similar comet tail conformations have been observed in Comet 1P Halley in 1910 and 1986, Comet C/1995-01 Hale-Bopp, Comet C 2006 P1 Magnotte, and Comet C 2001 V1 Neat. In addition, ejecta has been observed in Comet C 2001 A4 at distances beyond the water ice sublimation zone, which is 5 to 6 astronomical units. Such observations have been unsatisfactorily explained by 1. Latent heat release from amorphous crystalline water ice transitions, 2. Sublimation of frozen supervolatiles, 3. Comet fragmentation. Of course, the question is, what is the driving force for comet activity at such large heliocentric distances? In my theoretical framework of electron stripping, the driving force is a voltage differential between the comet and its surrounding plasma sheath. In this episode, we have seen 2 different articles reporting on negative charge nanograins traveling from the nucleus in a sunward direction and positive charge nanograins traveling from the nucleus in the anti-sunward direction. We have also come across reports describing increased electron beams and fluxes in the vicinity of the nucleus. The overall implication of these observations is that there is charge separation, hence the presence of a voltage differential as illustrated by electric fields accelerating charged particles. There is enough voltage differential for low ionization metals to be ionized, while residing in the lattice structure of minerals and silicates for the electrons to be stripped away of the lattice and accelerated. The results are electrons appreciably accelerated away from the surface of the nucleus, which we detect as ion beam influxes, causing ion impact dissociation on other volatiles, mainly because the associated electric fields accelerating the charged particles are filamentary in nature. Now, As the electrons are accelerated away, the metals in the lattice structure become positively charged and smaller in size, destabilizing the lattice structure to the point of collapse, upon which fragmentation becomes a dominant mechanism. This electron stripping process can be a source of both electrons and positive charged nanograins. In addition, because of the complex electrical environment, charge separation occurs, and in conjunction with charge exchange, negative charge nanograins can be expected to travel towards the sunward direction as previously discussed.
In episode 5, we delve into the fundamental question of comet origins and composition. One extraordinary revelation from the Rosetta mission is the discovery of abundant molecular oxygen in the coma of Comet 67P. This discovery was an enormous surprise for proponents of conventional comet theory. However, Dr. Anariba explains why this discovery is extremely supportive of the electrical theory of comets.
In episode 5, I provide a review of a recent article, quote, Abundant Molecular Oxygen in a Coma of Comet 67P, Churyumov-Gerasimenko, by Wheeler et al., where the detection of relative abundances of molecular oxygen is reported. The presence of molecular oxygen is surprising because it is not predicted by the current and dominant condensation sublimation model of cometary origin and composition. The latter, sent to Nature magazine, is well presented, and the observations are derived through direct mass spectrometric measurements with sufficient resolution, such as the double focus mass spectrometer from Rosina. Here are the relevant observations. 1. Local molecular oxygen abundances range from 1 to 10%, with an average of 3.8% with respect to water abundances. 2. There is a strong correlation between water and molecular oxygen relative abundances in the coma of Comet 67P. Molecular oxygen to water relative abundance ratios do not vary as a function of heliocentric distance and for a period of 7 months of observations. 4. Molecular oxygen was detected as close as 10 kilometers away from the comet's nucleus. In the backdrop of these observations, the authors put forth a series of well-thought mechanisms to explain the origins of molecular oxygen and water vapor within the condensation sublimation paradigm. Unfortunately, no explanations beyond this paradigm were presented. Here is a list of the considered mechanisms. 1. Photolysis, defined as ultraviolet photons capable of breaking molecular bonds. This explanation is unsatisfactory because, according to the authors, quote, instantaneous creation of the measured molecular oxygen by radiolysis or photolysis seems overall unlikely and will lead to variable molecular oxygen ratios due to different illuminated conditions. In other words, if electromagnetic radiation were the driving force behind molecular oxygen formation, then the molecular oxygen to water vapor ratios would not remain constant, which is not supported by the data. 2. Recent radiolysis envisions molecular oxygen production on the nucleus from the interaction of solar energetic particles with peak energies in the field of 10 millielectron volts. This mechanism will only be effective within a few micrometers of the surface. If it were in action, the molecular oxygen to water vapor ratios will have to decrease over time, as the top micrometer layers will be exhausted by erosion as the comet orbits the Sun. Furthermore, due to comet erosion rates, molecular oxygen production rates will have to be very high in order to be supported by the observed data. 3. Primordial molecular oxygen. Molecular oxygen was formed during the formation of the solar system and accrued in the nucleus of Comet 67P. This mechanism implies that higher temperatures are needed to produce significant amounts of molecular oxygen, suggesting the solar system accretion model formed from unusually warm molecular clouds. In addition, The solar system accretion model does not predict high oxygen to water vapor ratios values as observed. Finally, the solar system accretion model predicts the presence of ozone, which was not detected. 4. Radiolysis before the solar system accretion. Molecular oxygen is produced by radiolysis in water ices that are then trapped in voids where somehow hydrogen diffuses out, avoiding hydrogenation of molecular oxygen, increasing and stabilizing molecular oxygen concentrations, which can be incorporated into the nucleus. This is an unlikely scenario due to the high molecular oxygen reactivity and because ozone resulting from molecular oxygen radiolysis, as reported to be trapped in Ganymede's surface, was not detected. 5. In situ molecular oxygen production in a coma. The authors argued that the coma is tenuous and therefore may not afford the necessary collision frequency to overcome the activation energy barrier associated with required chemical reactions. Subsequently, the reaction of oxygen plus hydroxide yielding molecular oxygen and hydrogen remains unfeasible. This analysis holds only if we assume that chemical reactions are driven by electromagnetic radiation. 6. Long-term radiolysis after the solar system accretion. Molecular oxygen production from water by radiolysis produces hydrogen, oxygen, and hydroxide, followed by molecular hydrogen, H2O, and hydrogen peroxide rearrangement. However, at current erosion rates, Comet 67P will require substantial molecular oxygen diffusion into the comet nucleus from each subsequent passage around the Sun to avoid molecular oxygen earlier depletion. Moreover, galactic cosmic rays produce molecular oxygen only within tens of meters of the surface, which would have been already released. 7. Molecular oxygen production via solar wind surface sputtering. This mechanism is not supported by previous findings that show preferential solar wind sputtering in the northern hemisphere. In addition, the northern hemisphere does not contain water ice from which molecular oxygen can be derived. Finally, the molecular oxygen water vapor relative abundance ratios are independent of latitude and relative constant over 7 months. 8. Incorporation of primordial molecular oxygen into the cometary nucleus. Gaseous molecular oxygen incorporates into water ices in the protonebula, which rapidly cools down from more than 100 Kelvin to less than 30 Kelvin, trapping molecular oxygen in water ices. The last mechanism is the one favored by the authors. However, it can be highlighted that such a mechanism needs the presence of unusually higher temperature in young protoplanetary disks, which then undergoes selective rapid cooling. It is possible, but difficult to evaluate since no time scale for the cooling is given. Furthermore, molecular oxygen-rich grains will have to further accrete into larger bodies and then be trapped into the comet nucleus, all the while not reacting. But it is well known that molecular oxygen is rather highly reactive. Highlighting comments made on the European Space Agency website reveal the impact of the findings. Quote, "We weren't really expecting to detect molecular oxygen at the comet and in such high abundance because it is so chemically reactive. So it's quite a surprise," says Catherine Alward of the University of Bern and principal investigator of the Rosetta Orbiter Spectrometer for Ion and Neutron Analysis Instrument, ROSINA. Open quote, "The amount of molecular oxygen detected shows a strong relationship to the amount of water measured at any given time. suggesting that the origin of the nucleus and release mechanism is linked. By contrast, the amount of molecular oxygen seen was poorly correlated with carbon monoxide and molecular nitrogen, even though they have a similar volatility to molecular oxygen. In addition, no ozone was detected, close quote, says Andre Willer of the University of Michigan and lead author of the paper describing the new results in the journal Nature this week. The following quotation is telling. Andre Willer goes on to say that, open quote, the instantaneous generation of molecular oxygen also seems unlikely, as that should lead to variable molecular oxygen ratios under different illumination conditions. Instead, it seems more likely that primordial molecular oxygen was somehow incorporated into the comet's ices during its formation and is being released with water vapor today, close quote. The only reason in situ molecular oxygen generation is not considered is because photons are thought to be the only driving force for chemical reactions in the coma 67P. Obviously, under such circumstances, the phenomenon seems mysterious. Open quote. This is an intriguing result for studies both within and beyond the comet community, with possible implications for our models of solar system evolution, close quote, says Matt Taylor, European Space Agency's Rosetta Project scientist. It is clear that the correlation of relative abundances between molecular oxygen and water vapor indicates a single origin and release mechanism. The question is, which mechanisms? I propose a mechanism that allows for the simultaneous formation of molecular oxygen and water vapor, where the driving force is a voltage differential, such as an electrochemical method. There is plenty of evidence of the presence of filamentary electric fields accelerating electrons and ions in the vicinity of the nucleus, leading to charge separation, as has been demonstrated through these episodes. I'll call this mechanism molecular oxygen and water vapor formation by electrochemical means. In this method, molecular oxygen, superoxide, hydroxide, hydroxyl ion, and other chemical species are released into the coma by various mechanisms, such as electrostripping, solar wind sputtering, and solar heating. In this context, molecular oxygen can absorb a negative charge through charge exchange due to demonstrated high electron densities in the vicinity of the nucleus, followed up by protonation via the solar wind. Subsequently, water can then be formed via at least two pathways. Molecular oxygen plus hydrogen yields water, or superoxide plus proton yields water. In this theoretical framework, whereby the driving force is a voltage differential in the vicinity of the nucleus, the instantaneous molecular oxygen formation reaction that was deemed unfeasible becomes feasible when looked at from an electrochemical perspective, as the reaction can occur directly via gas phase collisions or be mediated via silicate catalysis on nanograin surfaces. In a general perspective, a voltage-driven chemical reaction mechanism looks promising, as it can explain the formation of complex chemical species such as water, alcohols, cyanide polymeric chains, sugars, amino acids, and others with satisfaction, without the thermodynamic constraint of low temperatures driven collisions.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info.